today we'll be concluding chapter 3, and so far we've um, defined Markov decision processes and the concept of returns and episodes, where we have a sequence of steps, and what we want to um, extract from an episode where a bunch of states are visited is this expectation of what the future rewards will look like. So here we define um, the the return as the sum of future rewards. And in this case, it's defined for an episode where it ends at this step capital T. So this is a finite sum. And then for problems that are continuing, we had noted that this sum could be infinite, in which case we have to introduce this discount rate gamma, which is a number between 0 and 1. And this guarantees that the sum is finite, as long as the returns themselves are finite. So we have sort of these two definitions. Of course, you could also just look at this as having a discount rate that is equal to 1, but a discount rate of 1 is only valid for an episodic task where we know the sum is finite. There is this little extra thing to note that we can actually write out the return and not worry about the fact of whether it's an episodic task or a continuing task, as long as we include the discount rate gamma. We have the sum to t, and then we can just allow t to be infinitely long if it is in fact a continuing task. But there's this caveat that if t is unbounded, then we cannot allow the discount rate to be 1. But as long as t is finite, for it's truly an episodic task, then we are allowed to select gamma 1, in which case we're in this situation where we have this sort of undiscounted return. In terms of the diagrams where we draw these like states and these trajectories, when a task is episodic, we note the terminal state with this square, this gray square, as opposed to the open circles, which represent the normal states. And then the special thing about the terminal states is that a process, once it's in a terminal state, can only return to that same state and get a reward of 0. So we normally don't write like this sequence of rewards will just continue on and be 0 when we know the task is episodic. Therefore, we don't have to include those rewards in the sum. But we could also, write down an episodic task and actually have the sum go out to infinity. It's just that most of the values will be 0 once we've reached the terminal step. So that's what's shown here, is that the sum, the reward sequence essentially ends once we reach the terminal state. But we could also think of it as continually revisiting that state. Okay, so does that sort of a quick recap of all these concepts? Is there any question about the definition of the return or the discounted return? Because the next section is really, it's going to end up being the most important concept in the book, at least for the entirety, or for most all of the book until the section at the very end on policy gradient methods. But every technique in the book other than that is going to make use of the concept of a value function. So it's here in this section of the chapter that we define the value function and the policies that are associated with a value function. So I guess so far we haven't formally defined what a policy is, but for now we're going to say that a policy is defined as a probability distribution for a given state. So here, we have a state S. So the policy distribution is conditioned on the state S. And then the variable it's over is A, where A are the possible actions that can be taken from the state. So the policy just tells you the probability of taking actions in that particular state. And the whole concept of the value function is a way to take all the information about what happens from a given state, like what we expect to happen in the future under a policy, and summarize all of that with a single number. And that single number is just the expected value of the return. So there are two value functions that are used throughout the book. The first one is just the state value function. And that's because it's only defined for a state. And it tells you, under the assumption that you are in that state, then what is the expected value of the return? Or in this case, the return is this sum. Here we're sort of treating the continuing case of the problem, but this also covers the episodic case where we just have all of the reward values after a certain point are just zero. But this is the natural way to write it out for a continuing problem. So this is just the definition. This is just expanding this expression using the definition of the return, where we have the sum here. And then this is conditioned on, at a particular time step, we're in state S. But that time step is not present in the expression for the value function itself, because it doesn't actually matter which time, when we visit the state. It will turn out that the value, there is a well-defined value for that state independent of what t is. And that goes back to the Markov property of these environments. And then the state action, or it's either called the state action or the action value function here, it looks almost identical to the state value function. There's just an additional condition here. And the additional condition is the assumption that we take this action in this state, a specific action, and that this action need not be the action that the policy would have selected, right? I mean, both of these are defined for a particular policy, pi, but the difference here is that we are saying that at the time step where we're in state S, we take this action A, and then for all future time steps, we would take an action according to the policy, which is also the assumption here. And that's what this expectation under the policy, like what this means is that along this trajectory where we get all these rewards, the actions being taken are the actions that are decided by the policy function, pi. Now there is this exercise here, just read it out. All of the derivations in this chapter become important. They all kind of build on each other and are used in later derivations. So here, this exercise is regarding actually like the definition of the policy function and understanding what that means. So the question is, if we're in a state S and we select actions according to the policy, then what is the expected value of the return? I'm sorry, of the reward that we get immediately, after transitioning from this state into the next state. And it's asking us to come up with an expression for this, which is expressed in terms of the policy function and the dynamics equation, which is what we sort of started the chapter with. This is the dynamics equation, which tells you the probability of any transition occurring in the Markov process that we're in, right? So this is the probability that given a state S and an action A, we transition into a new state S prime with the reward value R. So what we have to compute here is this expected value, right? If you can read this here, it's the expected value of the return of the reward on this step, given the condition that we are in state S. And we can expand this out just using the definition of the expected value here. So this is covering one part of the expected value definition, which is the sum over the variable in question, which here is the reward, times the probability of all of those rewards. Now, I'm handling the expectation under the policy here, right? Given that this is the reward for just the next step. So it's the reward assuming that the action selected in state S is given by the policy. And that is what is said here, that whatever action is selected at time t is, drawn from this policy distribution. Actually, this should say, sorry, this should be like this, to emphasize that this is, right, the probability distribution of actions given the state S. Okay, so then the question is, how do we express this probability? Okay, and the way we do that is, first of all, just note that this part of it where I'm just drawing the actions on the policy, we can just write this out by actually explicitly putting in the policy function. Right here, we're just accounting for all of the different actions that can be taken and doing a weighted sum of the probabilities weighted by the probability of selecting that action. Right? So here, I'm just replacing here like a specific action with this statement and then summing over the probability of those actions. But this expression is just, we have a shorthand for this, which was defined earlier in the chapter. And the shorthand here is just the probability of, well, actually, I guess technically we didn't define this distribution earlier in the chapter, but we could think of this as just the probability of a reward R given this state action pair, right? And then since we have this for argument function, we know that in order to get this, we can sort of go backwards a step and note that if we sum this distribution, right, this is like a bivariate distribution over the transition state and the reward. If we sum that over the transition state, right, that is the same as just reducing this to this distribution just over the reward value. So it's just a few steps of simplification, and we're just left with this probability. We've reduced it to just a weighted sum over some of the actions and using the action selection probabilities from the policy, and then a sum over the transition states, and we have the for argument dynamics equation. So now we just replace this expression up here, right? We already had, the only thing we have to add to this is take this sum over the reward values on the outside of this. And then you can also rearrange these sums here. I've just rearranged it so it's a little shorter, a little bit of a shorter expression where we just move this sum over R inside of here, right? Because this sum with the policy doesn't actually depend on the reward value. Okay, so this is like a more compact expression. We could also move the R in here and have, write this out as a double sum. But this is how you would compute, the expected value of the reward on the next time step. And intuitively, it makes sense because we're really just summing over all of the different possible reward values that we could get. And that includes all of the different actions that we could take, as well as all of the different transition states that we could end up in. And then we also have to, keep track of the reward value for each one of those specific cases. And otherwise, this is just a normal expected value calculation. But this will come up later where we'll sort of replace this expected value expression with this form of it, right? Where we don't have the expected value operator in here anymore. We just have sums over distributions that we already know the definition of. So does this make sense? Any questions about this exercise or either the derivation or the meaning of it?
Well, just the one question in the chat. You said that policies were probability distributions, but they sound like rules for taking action or doing the calculation.
So they give you the for every action available, it tells you the probability of selecting that action. So if the probability, it could be a deterministic policy, in which case, right, you would have a bunch of actions and the probability would be one, a value of one for the action that was the rule of which action that you should take. So in that case, the distribution collapses where you could say, instead of writing it as a distribution, you could just say, no, this is just a mapping from a state to a particular action that you take. But you could also have a stochastic policy where
Well, that's what I was. Yeah. Okay, you got it. All right, keep going. I'm sorry.
yeah, no problem. Yeah, but this definition of the policy includes both cases.
Okay, now
I was also wondering, will there ever be an advantage to a stochastic policy? I mean, if you maximize over the actions, really?
Okay, so yeah, in the case of finite MDPs like this, it will turn out that the optimal policy can be deterministic, and that we don't actually need stochastic policies to have optimal. We could have both. Yeah, that'll come later when we define the optimal policy. However, in the part 2 of the book, when we get to approximation, in the case of approximation, that's a case where we don't actually know precisely what state we're in because the state space is too big. Our policy function doesn't have access to the exact state. It only has access to some like parameterization of the state space. And in that case, there are situations where you actually do need a stochastic policy.
I see. You can use it for exploration. Okay, thanks.
Yeah, no, it's not. In that case, it's not because you need it for exploration. It's because, like, if you know everything about the problem, it's because of the constraint of not knowing the exact state. So that is what creates the need for a stochastic policy. If we are in this situation where we have a finite state space and we can compute like our policy function, we can define it precisely for each individual state, then yeah, we don't actually need stochastic policies. We're free to just, yeah.
Okay.
We could have them, but they're not necessary. That'll be defined more precisely towards the end of the chapter.
But under those conditions, aren't you assuming that the distribution of the data, which leads to those states, is not changing? If it
yes, that's the dynamic. So this dynamics equation here, this defines the environment, and we're assuming that there are these well-defined probabilities that don't change over time.
Okay. So then it won't be optimal if those change. That's what the question I tried to raise earlier.
Well, if these are changing, then we don't have a well-defined environment. But yeah, like part of the idea that this is a Markov process is that these are well-defined probabilities. Again, like these are just the probabilities of how the environment works. This isn't like our policy can change and be changing as we're training or learning. But yeah, we're assuming that the environment has probabilities like this.
Okay.
If the environment is changing through a cycle of some kind, then
that typically happens with time series data, right? There's outside forces that are involved in.
Yeah. So if those outside forces go through some kind of cycle where there's a probability of the forces being a certain way, like throughout all time, then we could still use this. And we'd be limited in how good we can do, but we can still come up with the optimal policy under the assumption that like we know the range of values those changes could occur in, but we don't know exactly when they're going to happen, right?
Yeah,
because that would just be
short-term stationary, right? And then you'd have to recalculate.
Yeah, sure, but yeah, like if it's truly non-stationary, where it's like changing in an ongoing way, where
then
even
you can't do anything.
Yeah, but even if like this, right? Like these are probabilities, so they don't have to be one. So yeah, we could account for problems where there are external forces and we don't know precisely what they are, but we do know the probabilities of them occurring, even though
like in a network, you have two busy hours, right? That happen where the traffic increases tremendously and that impacts interference and
Oh yeah,
noise
sure.
and
However, in the
we,
case, yeah, but in the case you're saying, if you really have things where there are specific hours in the day where the dynamics are different, that could also be part of the state. So, like if you include time, like the hour of the day, it would just make the state space larger. But right, we could have different dynamics according to what time of day it is, if that's actually part of the state representation.
that's a good point. All right.
Yeah. So that what we kind of went over this a little earlier in the chapter. Yeah, all these sort of issues come up earlier where we define this dynamics equation. But yeah, you can always, if you include enough information in the state, you can sort of turn anything into a Markov process. However, if it's too granular, your state space will start to explode indefinitely. But if you have time of day phenomenon, that's an example where, yeah, you could easily just like partition your state space into different times and still maintain this property.
Right. Okay. Thank
Yeah. Okay. So I guess we'll here, let's move on. So okay, we have these definitions of both value functions, right? But these on their own aren't that useful. And what comes next, starting with these exercises, is to derive new expressions for the value function. So the first exercise here, and maybe I'll just show it. I don't know. I don't want to just rush to the answer if anyone's actually done these and wants to share how they thought about it. But this exercise, the first one is to give an expression for the state value function in terms of the action value function and the policy function. So I don't know. I can go through the derivation and the answer, but if anyone thought about this and wants to, present something or ask a question about it, we can look at that first. But okay, if not, let's just look at the derivation of this. So the state value function, right? Here I'm just writing out the definition of it. It is just the expected value of the discounted return, right? Given that, right, at time t, the state is s. And the action value function looks almost exactly the same. There is just an extra condition here, right? This is the only difference. Now, when I first wrote this out, I just sort of skipped right to the answer because it does seem like fairly obvious, but this can get a little confusing with sort of conditional expectations and what all this stuff means. So here I've just written out a generic example of a conditional expectation problem. So, right, if you have the expected value of x, like this is just the definition of the expected value, right? We have the sum of x over the probability of x being that particular value. Okay. Now we can always take this, and let's say we have a joint distribution over two random variables here, x and y. We can always just like artificially expand this by saying, well, we have a joint distribution, but I'm just going to take the sum right over the second variable. And this is just the definition of a joint probability distribution, right? That you can just sum over one set of the probabilities. Now, this, when you define the conditional probability, so the probability of x conditioned on y, this is just the joint distribution divided by the distribution just of y, right? So similarly, like we can rearrange that expression and we can write the joint distribution as the conditional distribution of x conditioned on y times the distribution just of y. Now here I'm just rearranging the sum where, I have the sum over y and I'm just pulling out the probability of y and then leaving the terms that depend on x in this part of the sum. But notice that this sum now, this is another expected value definition. It's just that instead of the expected value of x, this is now the expected value of x conditioned on a value of y. And that just comes from like the definition of the expected value. If the probability distribution you're using has a condition, then that condition also appears in the expected value. Right? So here, I mean, we basically just rewritten the expected value of x in terms of the expected value of x conditioned on y, but we have to sum over y. So again, like, I mean, this might seem obvious and trivial. Like, you could just write this down without actually like proving it to yourself. But this just means that we can always add a condition like to our expected value and then recover the original one by just taking the sum right over all the probabilities of that condition. But that's exactly what we have here if we compare the definition of the state value function and the state action value function. We just added a new condition to the expected value. So that means that we can just get back to this. All we have to do is take the sum of this expected value over all of the probabilities of the new condition. But the new condition is just the action, right? So, and the probability of the actions is the policy function. So here, if we want to get the state value function out of the action value function, all we have to do is take the sum, the weighted sum of it over the probability of all the actions. Right? So, this middle part is just a derivation. It's just general purpose derivation, which you could use in the future. But these kinds of manipulations are done, all the time throughout this book and other books. But either you have the intuition for this, or if you don't have the intuition for this, you can just see it, what it looks like here. But this is like sort of the headline result of this. But does this relationship make sense to everyone? Okay. Good. So the next exercise is similar, but it's sort of the opposite of this, which is expressing the action value function in terms of the state value function and the dynamics equation. So this one ends up being a little different or a little bit longer, but this involves using this trick, which will come up a lot, where we have this expected value of the return conditioned on the state action pair. So we expand the return with its recursive definition, right? This is equation 3.9 in the chapter. Now, again, I'm going to use the definition of the expected value to write this out. So for this one, right, we actually already did this, right? The expected value of the reward. Well, actually, no. What we did up here was the expected value of the reward given just the state, right? And here, that's why we had the policy appear here. So here we don't have that because we've already defined the action, right? So we don't have to use the policy here at all. We just need to take the sum over all of the transitions that are possible given the state action pair. And then for this expression, I haven't really changed anything, right? All I've done is just separated this sum out, right? So we have this I've expressed as an expected value calculation with the probability. And here I have just left the expected value. Now, again, what I'm doing here is now I'm changing the condition again. This is kind of similar to what I did up here. So here, this is the return at the next time step, conditioned on the state action pair. But really, this really only depends on the next state that we're in, right? So this is a new condition. But then what we have to do is figure out all the probabilities of the transition state. So what this is doing is taking the sum over all of the different ways that we could arrive at different transition states, but it's still computing the same expected value, right? So it's the same logic that was used up here, right? Here, this is the dynamics equation. It still shares the same condition as before, but we're just advancing the condition forward one step, but then accounting for all the different, S primes that we could end up in. So, but now this new expected value, this is just the state value function at the transition state, S prime. I mean, we do have to account for all of the transition states here, right? That's what this sum is doing. But within each of those, we can just replace this expected value with the value function there. And then notice now, both terms in the sum have the same double sum expression over R and S prime. So we can just combine them into this single expression. So this is just saying that the action value function, we can get it from the state value function as long as we know the dynamics equation and we look forward, like for this particular action, we look at all the transitions that could occur from this action and sum over all those probabilities and use the reward for that transition and then the state value function at the transition state. Yeah, I mean, the key part of this derivation is expanding the return recursively and then figuring out how to get this new condition on the state S prime, right, which involves using the dynamics equation again. But, right, we're left with the expression we wanted, which is an expression for Q in terms of P and the state value function. So any questions about this or the derivation? Okay, so far we have expressed V in terms of Q, Q in terms of V. These were exercises. The next section of the chapter now does another derivation of the state value function. But the goal here is now to express the state value function in terms of itself. So to have a fully recursive expression for the state value function. And this is going to be the first of what will be several different Bellman equations for the value functions. And these equations are very important because they will actually be used in the future to come up with methods of how to actually calculate these value functions given an environment. But for now, we'll just look at this. It's a pretty short derivation for the state value function Bellman equation. We start with the definition, which is the expected value of the return conditioned on the state. Then we expand the return, right, into its recursive expression, going forward one step. Now, this next step in the book, this is exactly what it shows in the book. This next step is obviously like a lot to do. We're replacing the expected value in most places except for here. It really, if you want to see like this in more detail, it's really like the same thing as what I do here, but I do it in like a couple of more steps. But and also right here we have the expected value of R in terms of S. So for this part of it, like if you separate the expected value into these two parts of the sum, the first part here, we already did that, right, in exercise 3.11. That was just this. So you can see this expression right in here, right? We have R, P, and pi. They're all here. And then the second part of this is similar to this derivation step, where we change the expectation on S prime here, and we have to include the sum over the probabilities. But, when we're done, we end up then replacing this expected value with the value function at S prime. And we end up with this single expression which is an expression for the state value function in terms of itself, but looking at future transition states. And this diagram here, which is these backup diagrams appear throughout the book, but the open circles are states, and then the closed circles are actions. And what this is showing is starting at a state, right? The policy dictates the probability of all these actions. And then from the actions, the dynamics equation then tells you the probability of all the transition states and the associated rewards given that. So this backup diagram kind of summarizes this Bellman equation. If you look here, all of these open circles at the bottom, these are the values we get here, right? At the next, this is like the values of the value function that we're using are the values after this transition has taken place. And then all these lines we account for by just summing over all of the probabilities, right? Starting with the probabilities of the actions, which are up here. And then these lines are the probabilities given by the dynamics equation. So this, the first Bellman equation, actually the derivation of the action value Bellman equation is left to an exercise. But, I'll show that as well. But this is probably so far, probably like the most important single concept in the book for understanding how these techniques work, is understanding how we can sort of connect the states together with their values, and that the values of all the states are interconnected by this equation. Yeah, this will also define a system of equations and for a given environment. And then the value function, if you want to solve for it, the value function is the unique solution to this system of equations, because there will actually be the same number of equations as there are unknowns. So there is one unique solution to this. And to sort of visualize a simple example of it, there's this grid world example where this is the environment. So the environment is just, you can move on this grid in 4 different directions. There are no rewards normally, but if you end up either in state A or state B, you get a reward of either 10 or 5, and then you get teleported into either this state or this state. There's also a reward of -1 for trying to go off the grid, which is important for some of the states. But what's being shown here is this is the environment, and then this is the corresponding state value function for the random policy. So the random policy is one where there's an equal probability for taking any one of these 4 actions. Now, we haven't gone over yet how to actually solve or actually reach a solution for the state value function, but here we're just being told this is what the solution is. And then there's an exercise actually looking at this and seeing if you can justify what these values are. But I guess, yeah. First, before we do that, are there any questions about Bellman equation derivation, or then the setup for this grid world example? Okay, so if you look at this value function, like these values are actually given, I believe, with the assumption that the discount rate is 0.9. Yeah, because this is a continuing problem, right? Like it'll go on forever. We have the random policy. The reason why some of the values are negative is because we do get that reward of -1 for right actions that would have taken us out of the grid. And then here, like we do get, like once we're in state A, we do get, I guess this reward of +10 is actually already been accounted for from this state because we already receive it and then we start here. But you can see that like the numbers are higher in the states that are closer to the states where we know that we get this positive reward. Actually here, 5.3. I'm trying to think, why would this be less than 10 and this is greater than 5? I guess this is greater than 5 because there is some chance. Oh yeah, because we end up actually here, and then there's some chance we actually might. Yeah, well, we're actually just much closer here to the state B. So right, like this transition that takes us here, there's a much higher chance of here more quickly wandering back to this state than here we're transported much further away. Once we get down here, right, we're like we have this negative expected reward. So the chance of like repeatedly getting this reward of 10 is low, right? Even though this is already, yeah, a value of 8.8. But this next exercise is a way to check if you understand like how the system of equations works for the state value function. So, you know, it says like if this is in fact the correct value function, then we know that these equations hold. So it's asking you to just look at this state in the center, which is claimed to have a value of 0.7. And then there are these neighboring states. So if we write down the system of equations, we should be able to confirm that the value here satisfies this equation. Right, so if we look at this, we have all these probabilities we have to account for. Now, it turns out our policy is random. So because the policy is random, we can just look at all the individual cases and all the transitions are deterministic. So like once we decide to move to the right, we're guaranteed to end up in this state. So really, and we know that the reward is 0 for all of these transitions. So all of these cases end up looking the same, where we have a reward of 0 plus the discount rate times, right, the value at the transition state. So here, right, we have this transition state with a value of 2.3, 0.4, -0.4, and 0.7. So if you take these four different possibilities, and then we take the weighted sum where we just weight each one by 0.25. And if you calculate this sum, you would just end up with a value of 0.675. Right? And that, you know, rounded to the nearest decimal is 0.7. Right? So it said that there's only 1 decimal point of precision for all these values. So does this make sense to everyone? Is just how to use the Bellman equation by hand. Here, it's easier in this case.
Yeah, that makes sense, you know, given that, you know, the reward function and then the discounted value function.
And there's only one transition to account for all these actions. And that's just because for the grid world, the dynamics equation, right, is deterministic. That's why this P doesn't appear anywhere in these expressions, because P is just 1 for every transition here, once we define the state action pair. Okay, so then going sort of off of this grid world example, there's a comment that rewards are positive for the goal. They're negative for running into the edge of the world and 0 the rest of the time. Are the signs important or only the intervals between them? and then prove using 3.8. Go back to 3.8. 3.8 is just the definition of the discounted return. That adding a constant to all rewards adds a constant to the values of all states, and thus does not affect the relative values of any states under the policies. And then what is that value which ends up affecting all the states? Okay, so again, the idea is that like this grid world has been defined here with these rewards, and that if we just add a constant to every reward, same everywhere, how will it end up affecting the return, and then also by extension the state value function? Right, so this is equation 3.8, the definition of the discounted return. So if we add a constant to every reward, then right, we can just write this modified discounted return, G prime, as right, I'm just adding the constant C inside of here. Now we can separate out this sum, and it separates into two terms. The second term here is just the original return. And this is an infinite sum of, right, C times the discount rate. But this is a well-known infinite sum. It's just, you know, a geometric series, and it has this well-known expression, right, just C over 1 minus gamma. So the larger as gamma approaches, right, 1, this blows up to infinity, and the smaller gamma is, right, the closer this is to C. So remember that the state value function is just the expected value of G. So if we have all these G's, the only thing that happens when we add a constant is that all of the state values are just increased by this amount. So the point is the relative values between them are not affected, right? Which you'll see later why that's important. It ends up being important for it won't end up changing like anything about the optimal policy in that case. But for now, we've just derived that there's just a constant added to all the state values. So any questions about this exercise or the derivation? And no, yeah, this is a continuing problem here, which is why the sum is infinite. Okay, because the next exercise is a little more interesting. It's sort of a take off on this first exercise, which is, now let's say that instead of this type of task, we have an episodic task. So with a terminal state, like maze running, in maze running, you would have, right, like an exit where once you exit the maze, that the episode is over. And let's say you add a constant C to all the rewards in that task. What effect will this have on the values? And will it leave the relative values unchanged? So that's the question. Of course, since it's an exercise, you can probably infer that it will cause some difference. But before I show the answer, I'm just, if anyone thought about this or has any comment they want to make or question about this, you can ask it now. If no one has anything to say, I'll just show the derivation. I also have a sort of visual aid for this too. Okay, so here, I will just start showing this. So, right, in an episodic task, sorry, originally we had this, right? This is for a continuing task. The sum is infinite. In an episodic task, the sum is finite, right? It terminates dependent on this capital T, where T is the time step where the episode terminates. Okay, so now I'm just going to do the same thing. I'm going to add a constant C to all the rewards, and we separate out the sum. Again, we have two parts. The second part is just the original return. And now we have C times a finite sum of the discount rate instead of an infinite sum, right? Now this finite sum is of this form, right? It's the sum of something to the kth power from 0 to n. And this sum also has a well-known solution. You could just look it up. Here, this is just one way to derive it, but you can just first write out all the terms of the sum. Right? So we have gamma to the 0 plus gamma to the 1 up to gamma to the n, right? Note the gamma to the 0 is just 1. Now, if we multiply this entire sum by gamma, then multiply each term by gamma, and we just get gamma plus gamma squared, right? And then at the end, we have gamma to the n, and then gamma to the n plus 1. Now, we can rewrite this by adding a 1 to the beginning, putting a parenthesis here, and then subtracting the 1 at the end. So all I've done is add and subtract 1 to this. But now note that the term in the parenthesis is just the original sum. And then we have these extra two terms added to the end. So now we have an algebraic expression for the sum, right? We have gamma times the sum minus the sum, right? If we move the s to this side, is just these two added terms. We can solve this, and we end up with a solution that looks like this, right? Where we have, so remember the original sum, if this is an infinite sum, it's 1 over 1 minus gamma. You can see that here, right? If we actually multiply this by -1, this denominator is 1 minus gamma. And then if n is infinite, right, in the case of an infinite sum, this term goes to 0, right, because gamma is less than 1. So this ends up converging to this result in the limit, right, of n going to infinity. But we can now replace, right, this expression, noting that in our case, n, right, is actually big T minus little t minus 1. And then we can write out that our modified return appears to be the original return plus this expression, or this part in the parenthesis is what we had for the continuing case. And then now there's this extra term here. Now this extra term, if big T goes to infinity, this will actually go to 0. Or yeah. So if we're infinitely far away from the terminal state, this will limit to the result up here, where we just have a constant. But this extra term depends on big T minus little t, which is really how far away we are from terminating. And if you look at both of these added terms, here this graph is just what this factor is as a function of how far away we are from the end of the episode. So if we're really far from the end of the episode, this is also for gamma is 0.9. If we change gamma, the amount of this bonus value decreases. But here's 0.9, and then, depending on where the terminal step is, if the terminal step is really far away, right, this is the original bonus value we had for a continuing problem. And then as we get close to the termination, that bonus disappears to 0, right? And if the episode is pretty short, like here, right, the bonus disappears faster. So this is like the bonus we get from adding that constant C to the return. The amount it affects the values, right, actually depends on how far away we are from the end of an episode. But, right, if we look at what the state value function is, right, it's the expected value of G. And if we write out this expression, right, if we replace G with this modified term, right? We get the original expected value of G plus these bonus terms. Now, this part of it doesn't depend on the state in any way. But we have this term, which is the expected value of gamma to this power. And clearly this term does depend on the state, right? Because this depends on if you're in a particular state, how long do we expect, like how close is that state? How many steps do we expect to reach an end of an episode from that state? Right. So if we're very far from termination, we will receive like the maximum bonus value. But then as we get closer to the termination, right, if gamma is 0.9, we only get 10% of the bonus. And right, and that would be a case where, right, big T minus little t is just 1, right? So 0.9, this is 1 minus 0.9. Now, so it appears as though if we do this in an episodic problem, if we like add a constant, if we change the scale of the reward values by adding a constant, it does fundamentally change the problem. And another way to think about that is like if this was like a maze problem where there's an exit, if we add a value C to the problem and we have like a random policy, if we're far from termination, then we have more steps in which we can accumulate that bonus value that we've added, that value C. If we're close to termination, right, we're going to accumulate it fewer times. So it ends up boosting the state values that are actually farther away from the exit in the case of like a maze problem. But later on, we'll show how to actually solve, to calculate the state value function. But here, this is an example of one of those calculations. So here, this is just a grid world problem where this is the starting state and this is the goal state. Okay. And it's just like, this is showing on the left side, this is if the problem's episodic. So if the problem's episodic, right, once you reach the goal, the problem ends. And then this has a value of 0 because the state value function of a terminal state is always 0. Now, on the right side, this is if the problem is continuing. And if it's continuing, then once we reach the goal, we are teleported back to the start. And this can go on indefinitely. So here, there's a discount rate of 0.9. Now here, there's a reward. There's no reward boost. So in both cases, right, you get a reward of 0 for all steps. And then there's a reward of 1 for reaching here, right? And then because there's a discount like rate of 0.9, like this value, right? See, this is the closest value to the goal in both the continuing and episodic problem. So here, like this has the highest, or actually this has the highest value, but they're all pretty close in value, right? Like this is for the random policy. So, right, you're not guaranteed to enter the goal state from here. It just means that you're close to doing it. So, yeah, this top diagram, like the top 2 here, these are the actual values, the state values. What I've done in the bottom diagram is I've taken the smallest value, like the minimum value in the grid, and subtracted it from everything. So here, like this lower left corner, this is the smallest value, right? So here, everything's just been shifted down so that this lower left corner is 0. Here, I've done the same thing. I'm ignoring the terminal value here because that's always guaranteed to be 0. So now, if I boost the reward here, so I'm going to add like a bonus value, let's say. So here, I'm like adding a reward of 5 to every reward value. So now you get a reward of 5 for every step. And then the goal, when you reach the goal, you get a reward of 6. Okay. So everything is just shifted up by 5. Now you can see it does change the values, right? It makes them all higher. But notice I'll go back to the original solution. So we have in the continuing problem, right, this value is 0.058, this is 0.39. And you look here at the relative values. If I change the boost here, the relative values aren't changing, right? They're staying the same. I mean, there's some minor changes here just from numerical precision issues, but all the values, right, are staying the same, which is what we derived in the continuing problem. The relative values shouldn't change. But if we look at the episodic problem, here the highest values are the ones closest to the goal. But as I add this bonus value here, it completely changes the value function. Now the highest values are the farthest away from the goal, and the states close to the goal now have comparatively smaller values. They're still higher than they were like in the original problem, but the relative values have changed completely. And this is what we found, that for an episodic problem, you end up making it, right, it's more favorable to be away from the goal than it is to be close to it. If you add this, constant boost. Whereas, yeah, in the continuing problem, it makes no difference. So you can see here, I mean, if you trust that these solutions are correct, these are using, dynamical programming techniques later in the book. You can see if you actually do this and you compute the relative values, that, yeah, it doesn't make a difference for the episodic case or for the continuing case, and it does make a difference for the episodic case. So that's like the visual proof of this. But any questions about this exercise or the diagram?
Yeah, just one quick question. As you converge to the bottom of the bowl there shown, how does the initial state impact the algorithm? In other words, whether you're far away or go along a different contour line, is all the mathematics still the same, or?
I'm sorry, I'm having a little trouble understanding your question. So you mean if you go, are you talking about this grid world problem?
Well, you see the colored contour map?
You mean this?
Yeah.
Oh, well, this is a totally different example.
Oh. All right. Never
This
mind.
is a golf example. Yeah. But
well,
yeah,
I thought it was just projecting the algorithm convergence rate as a function of where the initial point was taken for.
No, this?
Yeah.
No, this is something totally different.
Okay.
But this is showing, I mean, there is an algorithm computing these values, but this is showing the converged values for everything. Like just like here, this is showing the converged state values. Right. So like what's being shown here?
How does this relate to an error function, minimizing an error function then when with the reward?
It doesn't. I mean, there's no error function here.
So you're just trying to maximize the reward?
No, actually, this is not right. This is computing the state value function given a policy. There's no maximization here. This is for the random policy.
That's later. That's later then. Okay.
Yeah. This is saying if we have a random policy, what are the state values? And if we have a solution, right? This equation tells us how to verify a solution, which is the point of this other exercise, right? One of the exercises was like verify that this value is correct, right? And you can verify it by applying these equations, right? Because
how would I use this then to debug my approach for reinforcement learning? How does this help me to know that if I'm not getting the results I want, what would I look for in this space to help debug my code?
Well, you know, this, I mean, this is really like a pretty like fundamental concept in reinforcement learning, but we haven't introduced all of the techniques and concepts of how to, you know, optimize a policy, for example. So I mean, the short answer is when you do like policy improvement, things like that,
Yeah,
you can use this to verify that if you're computing a value function for whatever your policy is at the moment, right, that value function should satisfy the Bellman equation. So when you do,
okay.
we'll see later with techniques like, you know, like value iteration or policy iteration, that you end up, you know, using these to confirm that you've converged to the right value function.
Okay, so what Python or R functions are used for? This is under the hood in those functions.
Oh,
That
I couldn't.
happens?
That's way. I mean, I don't know what. There's probably a lot of different packages that exist. This is just showing like the fundamental math of everything. I
Okay,
have my own
that's fine.
implementation. Like if you look at this notebook, actually, this single notebook has code implementing everything in part 1 of the book. So you could look at like how, you know, I implement it. But yeah, depending on who's coding it or what the package is, you know, exactly
Okay.
where this calculation is taking place, I couldn't tell you.
Right, right. Well, okay, ultimately, what I care a lot about is, you know, finding, well, what are the packages that'll help me implement a reinforcement learning solution, and then how do I debug that when I'm not getting the results I'm expecting? So that's what I was kind of hoping to get. But
From a single
that
session, I don't think
no, no,
any.
no,
So, yeah,
no.
yeah,
I
yeah.
know
No,
there's a
if you
whole.
look, yeah, that's an enormous question. It involves a lot of parts, right? This, again, we've already been through the book. We've recorded sessions on later chapters that cover
Yeah,
techniques.
yeah. This is my first time here.
Yeah,
And
I
I may
understand.
be speaking.
Yeah,
Yeah.
this chapter is just introducing like the really foundational concepts that will be used later in the solution techniques. Like
Yep, got
you
it.
know, so right now we're just talking about the state value function for a policy. And that's what's
All right,
being shown
thank you.
here. And you know, the importance of this exercise is important conceptually, because if you're designing a problem with rewards, it is useful to know that if you have a continuing problem, the relative reward values are all that matters, like between states. If you scale them all up or down by a constant, it doesn't matter. But if you have an episodic problem, the absolute values do matter a lot. And you can't just assume that the problem is going to have the same solution if you use like differently scaled rewards. So I think that is an important takeaway
Okay,
for this exercise.
that's helpful. All right,
Yeah,
thank you.
because again, like it's your, when you design a problem, like you may have like this dynamics equation may be given to you in some way. Likely what's given to you is more just how the state transitions work, or that might be obvious given the problem you're interested in. The rewards are really, you know, more up to you. And there could be problems where it's very obvious what the reward values should be. And there's other problems where those choices really dramatically affect the solution. So, but we'll get to that later when we look at these simple grid world problems. You know, these are just examples of rewards, like, or like the one I showed, you get to a goal state, you get a reward of 1, all the other rewards are 0. But okay, so we can look at, let's see, where were we? Okay, so we already looked at this. Yeah, so we're talking about scaling with a constant. Oh yeah, this exercise is just the derivation of, this is the Bellman equation for the action value function. And, you know, you can look at this on, it's similar to the state value one. I'm just expanding the expected value and doing the same kind of tricks we did before. So we don't have to belabor it here, but this is much less commonly used, at least when it comes to dynamic programming. So yeah, this is the recursive expression for the state action value function. Now, wait, this exercise is asking, oh yeah, okay. So there's actually a backup diagram associated with this exercise. So the idea here, actually, I mean, we already kind of looked at this, but this is showing, if we have a state, we have the different actions. If we know what the state action values are here, then we actually already had an exercise where we wrote this down. But we can write the state value function as an expected value of the action value function, right? Because we end up transitioning to all these states, and depending on what action we pick, right, like these have to be consistent with each other based on the definition. So the state value function is just the expected value under the policy of the action value function. And we can also write that down, which I think I already did in an earlier part of the chapter, as this weighted sum of the probabilities for the state action value function. And then there's a similar backup diagram, right, for the action value function where, now we're starting with the state action pair. And then we have the dynamics equation giving us the rewards and the transition states. And then here for this exercise, we have the expected value of the immediate reward plus the discounted state value at the transition state. And that's what's being shown here. So this equation is just the equation that represents this backup diagram, right, where we have the reward, the transition state, and the value function where we end up. And you can also write this out again if we expand this expected value, right? This is just writing the expression out, removing the expected value operator, and replacing it with sum over probabilities. Okay, so anyway, there's a lot of different equations and manipulation, but it's important to have access to like all these different forms of the value function and expressing them in terms of each other, because they become useful later on when we derive other things. But okay, any other questions about this or these two exercises? Okay. So the final part of the chapter, finally, is getting to the optimal policy and optimal value function. And this comes back to what is the goal we have of reinforcement learning. And the goal is to maximize the return, right? Where the return is the sum of future rewards. So what does that mean? Now, there's some claims in here which aren't like derived or justified until the next chapter. But for now, we'll just take it for granted. So there's this statement that we can rank policy, like we can rank value functions. So once we define a policy, that defines a value function. And we can rank policies by comparing their value functions. And it will turn out that there is a particular policy, or we can make the statement that a policy is better than another policy if and only if its value function has a higher state value at every state than the other policy's value function. Now, it doesn't have to be strictly greater. It could be greater than or equal to. So there's always this equality operator. So we may have two equally good policies. Okay, so it's like here, right, we have the value function for the random policy. So if we were to say that there is a policy which is better than the random policy, and we computed the value function for it, all of these values would have to be higher than their corresponding values, or higher than or equal to. Okay, so that's our goal. Our goal is to find an improved policy, a policy for which the state values are better everywhere. And it's important that, right, this is for all S, right? So when we improve a policy, the claim is that we don't have to make any compromises. Like, it's not like we're improving the behavior in some states and it's getting worse in others. The claim is that for like a finite MDP like this, that the policy will be superior or as good or superior in all states. Now, because we can order policies like this, that means that there is one particular policy or family of policies which share the optimal value function. And what we mean by the optimal value function is a value function which has the highest possible value at every single state. It means that for any other value function that is defined by a different policy, like whichever policy you choose, its value function will either be equal to or worse at every single state in the problem. So this is the definition of the optimal state value function. It's saying that out of all the policies that we could look at, it is the policy which maximizes the state values at every single state. And then similarly, we can write down the same expression for the state action value function. This just means that if we're forced to choose a particular action, but then, after that, we're free to follow the policy, that there is similarly some action value function, which is maximal everywhere. Okay, so that's the concept. We haven't said exactly how we get there or what that means, right? Because here, this is a statement about choosing, like looking at all the entire space of possible policies and choosing the one that maximizes the value function, right? But we will show later how like there is an equivalent thing that we can write for this, where we can actually come up with an expression for the optimal state value function. But so far, is there any question about this claim here of what we mean by the optimal value function? We can also express the optimal state action value function. So here, like so far, we're making a little progress here. We're taking advantage here of the fact that we know that if we select an action, right, that implies something about the reward we get on the next step based on the dynamics of the problem. And if we take this expected value, if we already have the optimal state value function, we can just use that. Like this has to be true just based on the definition of what the action value function is compared to the state value function, right? Because we're claiming that there is some policy that we could follow that would produce this optimal value function, right? So it's saying here, okay, we'll just follow that policy at the transition state, right? And then if we account for all of the different reward values that we could get after selecting action A, this is one way of computing the optimal action value function. Of course, this is assuming we already have the optimal state value function, which we don't know yet. Okay, but the next part of this is, again, it's going to use the relationship between the two value functions to arrive at an expression that we can actually use to think about what the optimal state value function is. So we're gonna end up using the Bellman equation. Of course, we can only apply the Bellman equation that we've written down by selecting a policy, right? Because here, actually, where is it? Right, here's the Bellman equation for the state value function, right? And it's defined for a particular policy. So we're going to say, let's say that the optimal policy exists, or there is one that exists. We're going to call it pi star. So pi star is some policy that ends up producing the optimal value function. So if that exists, then what properties does it need to have? And the first statement here is that we've already said that these state values are as high as they could possibly be. And that means that if we pick a state and we know we also have the optimal action value policy, this has to be the maximum value of this across all the actions taken. Because if there was an action that produced a value higher than this, then this wouldn't actually be the optimal state value function, right? Because it would mean that there was a different policy that selected a different action that ended up producing a higher value, right? So this first step is just sort of, right, the logic of what we mean, like the original definition of the optimal value function. Now, right here, this is just the definition of Q. Right here, we're writing down the expected value under now the optimal policy, right? We already did this under this condition. This is just expanding the return, right, with the recursive definition, right? And now, we had already used this expression, right? We already had this expected value before, right? When we moved between the state value function and the action value function. It's just now that we're assuming that the expected value is under the optimal policy, not just some random policy pi, right? So here, right, we can end up replacing this expected value, right? This is the expected value of the return on the next time step under the optimal policy. But that is just the optimal state value function at the transition state. And now, right, we have this conditioned on S and A. This expected value we computed in that earlier exercise, remember, where we replaced this with this sum, right, over the probability transition function, right, with S and A. And then here, right, we already did this too, right, where we move this condition forward one time step. But the consequence of that was also having to take this sum over the transition states, which is here. So really, like, this is the most important step. And then all of these steps, right, there's this maximization operator out here, but all the steps in here were already done with a particular policy pi. It's just now we're doing it with this optimal policy, pi star. You can also, again, like, this is less commonly used, but you can also derive a similar expression for the optimal state action value function here. In this case, it's actually much, I don't actually know if this is a full derivation or makes use of this already. Yeah, but this process of moving back and forth between the two types of value functions is very common in these derivations. And note, yeah, actually this step here, right, we had actually already written this out here. So here they do it in a few different steps, but what we end up with in here, you can actually get from this as well, right? This is, right, R plus gamma. So this all follows from both, the Bellman equation we had and the assumption that, there was some policy that existed. But the point of this expression is that if an optimal policy exists, then its value function will have to satisfy this expression. And if you compare this, so, I mean, this is called the Bellman optimality equation for the state value function. And if you compare it to the Bellman equation, the only difference between, right, 3.14 and this is that this sum over the policy is replaced now with a maximization operator. And that's because here, right, there's no policy actually referenced here, because whatever the policy is, it doesn't matter. This value has to be the maximum of this if you consider all of the possible actions that can be taken. And the origin of this maximization operator is the statement that, right, the optimal state value has to be, the highest value that it could possibly be. So like there can't be another action that would have produced a higher value. But right, this generated a system of equations where we could solve for the state value function given a particular policy. This also produces a system of equations, but now we have this maximization operator instead of this sum over the policy probabilities, which does make this, there'll be an example later of what the system of equations actually looks like for one of the earlier examples. But again, it will be a system of equations with, one unique solution. And then the point of doing this is that once we have this value function, right, then the optimal policy is actually easy to derive. And in fact, it's even easier to derive if we have the state action value function here, right? Because this is saying, what are all of the possible, like what is the optimal value if we consider all of the actions? Like if we are forced to select a particular action. And that means that we can just look, if we're in a given state, right? We can just look at the values for all the actions. And then the action that we should select to follow the optimal policy is just the action with the highest value, right, of these values. Now, it turns out, like we wrote up here, or maybe, it might be derived later on. But yeah, we can also use the state action value in a similar way. It's just that we also have to use this dynamics equation. And there's a later, I think it's in one of the later exercises, but we can see that we can actually express this back, again, another transformation of the expression, but we can express this in terms of this. And once we do that, right, really to figure out the optimal action to take, we need to have this quantity and just, see what it is for all the different actions. And, we can actually derive this from the state action value. Yeah, so this, like ideally we would compute this because this gives us the answer directly. If we have this, we also need to have more information about the problem. But the point is here, I made this statement bold in here, but right, this is obviously more information to represent. Here we just need a value for every state. Here we also need a value, right, for every state action pair. But if we are able to calculate that, then it turns out we can just look at this table of values directly and see what the optimal actions are. And we don't need to know anything about the possible successor states that we end up in, right? So if we look, like here, right, this backup diagram showed the relationship between the state value function and then the state action values, or sorry, actually, it's better to look at this one, yeah. So if we look at different state action pairs, right, we can go down, and then if we have this state value function, we can end up computing like what these transition state, like what all these values are and add them up for all the different possible transitions. And that way we can end up deriving, like recover what these values are. But in order to do that, right, we need to know how these dynamics work. So we can't just, look at the values directly like we would here. So, there's a system of equations here. We can solve it directly. The way to arrive at solutions actually comes in the next chapter. But, oftentimes like directly solving the system of equations is not best way to approach these problems. So there's techniques that involve sampling. When we do want to solve the problems directly, we'll introduce it in chapter 4, but it's better to use these dynamic programming techniques that will make sort of use of the Bellman equation and the Bellman operators to do that. Yeah, so what remains in the chapter, there's sort of conceptually understanding how the optimal value function works with this golf example. And it might be good to just quickly look at that. Here, let's see. This golf example, the point is to kind of show examples of how all the different, like what all the different value functions mean. So the idea here is that like we have a golf course, we're assuming that actually like swinging the club and doing all that is handled by some other system. Like the player knows how to, aim and swing the club. And the only action that needs to be taken is the decision of which golf club to use. So there's 2 golf clubs. There's a putter and a driver. And the policy would basically tell you which club to use in which situation, where here the state is where you are on the golf course. Now, this looks like it's sort of a continuous state space, but we can look at it. These like contour regions tell you sort of where the states begin and end. So what's shown at the top here is the value function for using the putter. So it's saying if you use the putter and you only use the putter, what are the state values? And here you get a reward of -1 for every stroke that you take. So these numbers just tell you how many strokes you need to make before you sink the ball in the hole. So what this means is that if you're anywhere on the green, you can make the shot like with the putter, you can get in the hole on the next shot. And then every region outside of that is just an additional stroke that you need to take to reach the hole. And then if you're in the sand trap, the putter is unable to get out of that. So we see these little regions where here you have to go around the sand in order to get to the hole. Okay, so this is the value function of using the putter. Now, what's shown down here is a little different. This is supposed to be the optimal action value function for using the driver. This is saying so the optimal policy is the policy that chooses the best club in every situation, right? But this is saying for the initial stroke, we don't use the best club. We always use the driver. And then for every shot after that, we use, whatever the optimal policy says. Now, for these states out here, like if we're this far away from the goal, clearly using the driver here is best. So this contour here will actually match the optimal state value function, right? Because the driver is the best club to use. And we can see that when we get close to the green, that, right, this -2 region actually goes to here, and then the -1 region is very close, meaning that we can only make the putt, successfully with the driver if we're much closer to the hole. And that if we're here, using the driver is clearly not the best action to take, right? Because we already know that with the putter, we can make the shot in 1 shot. And here with the driver, we need at least 2. So there's this exercise. The first exercise is to describe the optimal state value function for the golf example, or draw it. To make things a little easier, I kind of drew this out a bit. So here, this is like what the example looks like in the book. So, right, we have Q star using the driver. And what we want to know is V star, right? We want to know the optimal state value function. Now, we know that its value has to be higher. Like whatever this is, its values everywhere on the course have to be larger than any other possible policy that we could have, right? This in particular is a policy that uses the driver first. Now, if we compare it to the putter, right, we know that like we can't do any better than -1. Like that means we're going to make the shot like on the next shot, right? So we know that like using the putter on the green is already optimal. And clearly here with the driver, and then, you know, for all this region, if we're using the putter, the best we can do is 2 shots because we can't make, get it in the, like, we can only make a successful putt from the green, right? So there's no difference here in this region between using the putter or not. Like we know that if we're off the green, we can't do better than -2. So, right, if you look at this expression, right, we already knew this where the optimal state value function is the maximum of this if we maximize over all actions. Now here, we're only given one of the actions, but we can infer from the other diagram if that is actually a maximal action. So if you compare these 2 diagrams, we know that anywhere off the green, the driver is the best thing to use, right? Because its value is greater than or equal to all of the values here. So the only problem is once we're on the green, clearly the putter is better. So for this first question, the optimal state value function is just identical to this, but we end up getting rid of this contour and just replacing it with -1 anywhere on the green. And then everywhere else, like this is -2, this is -3. So it's the same as this, but all the values on the green are -1 because we would end up using the putter on the green, and we already know that that is a value of -1. So does this make sense, everyone, for the first, or for just the optimal state value function? Because then the next question is a little more complicated. It's asking, what is the optimal action value function for the putter? This is like a little convoluted, but the idea is that we have this, right? This is the optimal state action value function for using the driver. Now, the putter, so here I've like drawn over this diagram for the, sorry. Okay, so I've drawn over the diagram that previously showed the putter state value function. Okay, so we want to know what is the optimal action value function if we're forced to use the putter on the first shot. And to figure out how to get this, we're going to use this expression for, right, so this is how you can express, right, the optimal action value function in terms of the state value function, where we have the expected return from the initial action plus the, here there's no discounting, right? It's just the gamma is 1 and the value at the transition state. So because we already know the optimal state value function down here, we can try to reconstruct this. Now we know R is always -1, right? So if we look at any spot on the course and we want to know this value, we can always get it from this value. If we say, well, wherever we are on the course, if we take a shot with the putter, where do we end up? And then wherever we end up, we would take the value from here and add -1 to it. Now we can infer where we end up with the putter looking at this diagram, right? Because we kind of know these contours define how far you get with the putter. So what I've drawn on here is if you take this -2 contour and like superimpose it on the diagram here, basically, any putt that would bring us to here, then the state value or the action value at that location would be -3, right? And then similarly, like we know that if we're like here, then right in this -2 region, we can make a putt and get on the green, and that's going to remain -2. So everything here labeled -3. So basically, if you look at this line here, this entire region out here, including this, these all have a value of -3. And the reason for that is this contour represents all of the spots on the course where if you make a putt from here, you would end up inside of this -2 contour, right? So then the value is going to be 1 worse than that because we sort of like waste a putt getting from here and staying in here. And then, we know that anything here is going to share the value of -2 because from here we can get like we end up on the green from, and also this is already the putt. So the only difference here is that some of these values end up being better because, right, this is -6 because we're forced to putt the entire way. But now this outer region becomes -4 because if we putt from here, we end up in this -3 region. And then we know from here, right, we can make it within 3 shots. So it's just 1 worse than that. So I'm sort of like, if you look at the equations we've already derived, this is sort of like asking if you only have partial information, how do you like reconstruct, some of the value functions from the other value functions? But I know it's a little cluttered on the diagram. If you look at the notes, I also like wrote out just in text a description of what the contours look like. But the basic like headline answer is like the worst value is -4. And then places like if you're in the sand trap, right? Like the sand trap is more obvious to figure out because we know that from the sand trap we can't leave. So we putt once in the sand trap, we're still in the sand trap, and then we know that, right, the optimal value that it takes 2 shots from the sand trap, right? 1 shot to get on the green, and then the next shot you get it in the hole. So we end up just wasting that first putt, and then all the other contours just follow from where you end up. So yeah, I hope that's a little helpful. I know this example is like a little confusing, but I think it helps with understanding like the relationship between the 2 different value functions. So any other question about this golf example? Okay. So these remaining exercises are just yet further variations of value functions. I think it's useful to see them written out. Of course, they're all written out here in the notes with different sort of amounts of derivation. So you can look at them later. I mean, this last one is like asking you to rewrite a bunch of equations. I think probably the most useful of all of these to make note of is actually this expression, right? So this is the Bellman equation we had for the optimal state value function. And this is equivalent, but the important difference here is that we've now separated these 2 terms out. So here everything is combined together, and we have to use this full dynamics equation. We have like all the probabilities of all the rewards and the transition states. And you can show here, right, this RSA, like this equation, this is the expected reward when you take with this state action pair. And, it has an expression in the form using the full dynamics equation. And this is the state, is the dynamics equation where we remove the reward by summing over it. So this is the probability of a transition happening with any reward value. The reward doesn't matter. And what's nice about this is that it actually reduces the amount of information we need about the problem. So if we want to solve this optimality equation for the state value function, we don't actually need this full dynamics equation if instead we only know the expected reward and this partial dynamics equation where we just know the probability of a transition without all the transition states, then those two pieces of information are actually enough to write down the system of equations. And it does make it a lot easier. It also makes it so that you don't actually have to have this reward space fully defined where you have a discrete space. If you just know for certain what the average reward is for different transitions, even if that average is made up of a continuous distribution, it doesn't matter. You can just replace this whole thing with this average reward value. But then all these other expressions are useful in their own way. The only other exercise I'll go over is this 3.22 because it is kind of interesting. The actual solution is not very long, but it's asking you to consider this problem where you can choose to go left or right at the top here. So you start at the top, you go left or right. If you go right, you get no reward, you end up in a new state, and then you get a reward of 2. If you go left, you get a reward of 1, and then on the next transition, you get a reward of 0, right? So this side actually gives you a larger reward value, but it's delayed 1 step. And this side gives you an immediate reward of 1. And the question is, which policy is optimal depending on the value of gamma? And you can figure this out by writing out the reward sequence. So if you're starting in this state, well, the first question, okay, so if gamma is 0, then you only care about the immediate reward. So obviously the left action is preferable. That's easy. But let's say gamma is not 0. So then if we go left, we have this reward sequence where we get an immediate reward of 1, then we have to wait a step, and then we get another reward of 1, and we're skipping a step each time, right? So we have this sum of gamma, but all of the odd powers have been removed. And similarly, if we go to the right, we get a reward of 2 after a step. So we have the same sum over gamma times 2, but all the even powers are removed. So we can compare these two sums, and we can see that if we go to the left, then the expected return is 1 over 1 minus gamma squared. And if we go to the right, it is 2 gamma over 1 minus gamma squared, which is just 2 gamma times the left return. So from here, we can see that as long as gamma is greater than 0.5, then this multiplicative factor is greater than 1, meaning we get a higher return. So if gamma is greater than 0.5, it's better to go to the right. And if gamma is less than 0.5, it's better to go to the left. Other way of saying that is the larger the value of gamma, then the more benefit we get from delayed rewards. And the smaller gamma, the less benefit we get from delayed rewards. So it's better to get rewards earlier. But this is a very simple example of a problem where the discount rate actually affects which solution is optimal. And we didn't compute the values of these states either, but it will turn out that all 3 of these states, the optimal value, does depend on gamma. And that, if gamma is greater than 1, because you end up getting this continuous reward cycle throughout the problem. So if gamma is greater than 0.5, it is better to go right. It doesn't matter if you're here, right, and you get no reward, you still want to go right when you get to the the top part here. And similarly, if gamma is less than 0.5 and you end up here, you already get this reward of 2 on this step, and then it's still better to get the reward of 1 faster, even though it locks you into getting a lower reward for more steps. That initial step is the most important one that matters. So this is an interesting problem for later because it actually shows the difference between finite MDP solutions and approximate solutions, which happen later, where if we don't have a well-defined solution at every state, then we can't make these same kind of strong statements about a policy being optimal. Like here, we define the optimal policy as one in which like the value function is best at every state, right? And that only has a meaning if we actually like know and can visit every state and know what they look like. And we'll see later in the book that when we have problems that we can't treat as finite MDPs anymore, then we no longer have like the freedom to, say we're optimal at every state. We have to come up with other ways of defining what's optimal, which ends up actually not being optimal by this strict definition, if we could look at all of the states. But yeah, I think, if you want to on your own, you can review like all these other derivations, these other forms of the equations. We'll see. Like I already mentioned how like later in the book we deal with problems where we don't actually have to store a value for every state, but for now we have problems that are small enough where we can do that, and these definitions work. And then in the next chapter we actually talk about algorithms that we use to find both the policy value function and the optimal value function. So we'll cover that next time, or at least as much of the chapter as we can get through. But yeah, these two chapters, like 2, 3, and 4, kind of form the bulk of the theoretical foundation for optimizing finite MDPs. And then everything that comes after this is either approximate solutions or estimated solutions where we sample, or approximate solutions where we have to, form functions that parameterize the state space. So yeah, I hope people, I think probably for most people, the next chapter will be more interesting because it actually shows you like how to solve the equations, but you can't use any of the techniques in this chapter until you've derived all of these relationships like between the value functions here. So do that next time. And then, if anyone has any questions about the end of this chapter, feel free to ask now. If not, we'll just, continue next time.
I'm sorry, just one quick question. I was looking into another article, and it talked about deep Q learning as far as the Bellman equation. Are you familiar with that terminology?
Yep. Q learning is a technique from part 2 of the book, but it usually involves a situation where you're coming up with approximate solutions, and you have a function that you're using to parameterize the state space. Or actually, wait, no. Q learning also. Let me just look at the table of contents here. I think they do still call it Q learning when it's done in the finite MDP setting. Let's see. Sorry. Q learning is a sampling technique that you can use. So it's a way to have estimated solutions. It works in cases where, like when you have this dynamics equation for the problem, like you don't know this dynamics equation, you have to actually sample. So it's another just sampling technique. When you talk about deep Q learning, that implies there's a neural network you're using to parameterize the value function.
Okay, got it.
So
I heard.
you don't have to do. You don't have to do deep Q learning though. normal Q learning just is usable in finite problems, and it involves just having a table of values that you update. But the
Okay.
Q part, of the Q learning, if you want to know the connection, it
Yeah.
comes from this, like the action value function is the Q, right? So it's Q.
Oh,
So you're trying to learn these action values and then derive the policy from the action values. But instead of doing it exactly, you have to apply this estimation technique and sample from the environment. When you have deep Q learning, you have a function like this, but instead of knowing these action values, you have a function where when you plug in the state action pair, it gives you a value. But it's like it's a function with parameters. It's not like just a table of values, because the state
right.
space is too big. You're unable to store all the values. So you have some sort of way of compressing the values and approximating them with a function.
So is it like a quantization error that occurs, or how do you,
No, it's
or is
not
it
a
like,
quant. It's really just a function that it's like, if you represent the value function, like this is like you have state action pairs, like in theory, you can just store this as like a table, like a 2x2 table, or like a 2x2 matrix. Now, if that space is too large, or like the matrix would be too big, then you can define like a function over that space, right? Like
okay,
a
right.
two-dimensional function where you input two values. Now, depending on how that function is defined, it could be a really terrible approximation, or it could be very
Yeah.
good. Like if your value function is very simple, it may be very easy, but neural networks tend to be very good at this kind of interpolation. So if your value function has some like smooth properties over the space of state action pairs, then your neural network might do a good job of approximating that. But yeah,
Got
the
it.
error you end up with is entirely dependent on the constraints
fit.
of the function you're using.
Yeah.
Yeah. So the dynamic programming chapter, it really does like introduce dynamic programming. There's no background needed, but I think a lot of the concepts of dynamic programming ended up coming from this subject matter anyway. So yeah, it doesn't require any like previous background on that as a standalone topic.
So we're going to start on chapter 7 next. Is that what you said?
No, 4.
Oh, 4. I'm sorry.
Yeah, we're on 3. 4 is dynamic programming. So basically 3 and
I
4
don't know how
go.
I came up with that.
Okay. Yeah, 3 and 4 go together very closely. 3 introduces all the math and definitions of the value functions. Chapter 4 is entirely focused on how to calculate solutions.
All right.
And then it ends up solving some like specific problems, some example problems. So yeah, we will.
And when is this next meeting going to be?
It'll be in 2 weeks. All the meetings are so far they've been on 2-week intervals. Yeah, this group, like this meeting, is part of a larger group that also does paper discussions on the other weeks. So you could go to different topics. Lately it's been mostly focused on like generative AI papers.
And are those papers listed in the
in the meeting description? It won't be in. If you look at the group that I posted this under, you'll see the other meetings. I don't know if the next meeting's actually been posted yet, but you can check there. But
perfect.
Chapter 4 is the only remaining chapter that doesn't have recordings for it. So if you are curious about chapter 7 or any of the other chapters,
well, I'd be curious about the paper reviews also.
Yeah, you can look those up just on the meetup page.
And can people suggest a paper and then they vote on it to review, or how does that work? Or is it all you?
Oh, no, I don't. I have sometimes presented papers, but no, actually I usually don't. And there are other people that have presented papers, and there is a way of voting and suggesting papers. There's also
Okay.
a Discord channel you can join to ask questions.
Oh. All right.
Yeah.
Thank you very
Um,
much. It's great.
Yeah, sure.
You have
No
a
problem.
very deep knowledge, detailed knowledge of this field.
Yeah, well, at least insofar as the textbook goes. But yeah, if you're interested in the code or how to, I mean, I tried to there are other things you can look up for this type of material, and usually, oftentimes people will use packages and stuff because a lot of these techniques are already coded into reinforcement learning packages. But because the book is sort of aimed at building everything from the ground up, the code I have, it doesn't use any external package except for like statistics or basic, like really basic things. So
Right.
if you look at the code, you should see at least one way of implementing all this stuff. So yeah, thanks for coming. I don't know, does anyone else have any other questions? Oh, okay. Well, if not, thanks for coming, everyone, and yeah, hopefully see you next time for chapter 4.